This is Physics Lab number 5, Choose Your Own Adventure. So, a slinky at equilibrium is dropped. This is the video I chose to use. The goal was to analyze the motion of the falling slinky as it dropped from equilibrium position, track the motion of the falling slinky using Tracker, which was the experimental model, and then use GlowScript to create a computational model that accounts for drag force, gravitational force, and tension force. Finally, I compared the experimental model and the computational model and noted similarities and differences. The overall results showed that the computational model was quite similar to the experimental model. So some important physics concepts used in this lab were Newton's second law and the net force equation, which is change in momentum over the change in time, which can also be rewritten as force equals mass times acceleration, which can also be written as F net equals mass times acceleration, which is what I used. The velocity update, which is derived using the net force equation, and position update, which is derived using the velocity update equation. Here are some free body diagrams from the experiment. So before the top of the slinky reaches the bottom of the slinky, the force of the slinky and the force of gravity are equal and opposite, so net force equals 0. This equals 0. And after the top of the slinky reaches the bottom of the slinky, this is condensed, there's a slight drag force acting on the slinky, but the force of gravity is greater, causing it to fall. So in this case, net force is equal to the force of gravity plus drag force. The system in this experiment was the slinky and the hand dropping the slinky, and the surroundings was Earth and everything else. Here's Tracker. So in Tracker, I set the calibration stick to 1.75 meters. The origin is set at the ground to where the slinky reaches, and the tracker data begins when the object is released from the hand. So you can see it playing through, and I just skipped to the end because it's pretty long. And you can see the bottom of the slinky and the top of the slinky are together at this point, and it's a pretty constant change in Y position right here. The initial conditions I used for the computational model I used from Tracker. I got at this point that the initial position was around 0.5 meters, and the mass of a slinky is around 0.25 kilograms, and again, calibration stick set to 1.75. Here's the GlowScript. Here's part of it. So when t is less than 1, this is when the top of the slinky hasn't yet reached the bottom. I made use of force equals mass times acceleration, and tension in this case equals gravity, so F net is just gravity plus tension, and you'll see later that the bottom of the slinky does not move, and then velocity update, position update. When the slinky does begin moving, it stops, it hits the ground at 1.57 seconds when I did it in Tracker. And I use the same equation again, so force of gravity equals mass times acceleration, which is gravity. I use drag force, and the net force is force of gravity and drag force. And then here again is velocity update and position update. Here's what the GlowScript looked like. And I also used B equals 2.6 for the proportionality constant for the magnitude of the drag force. There's the part before it starts moving, when the forces are equal and opposite, and then here is when it starts to move. And here's what it looks like when it runs. It's just a ball for simplicity's sake. And you can see that here, it's pretty stationary and then it goes down. Here's what all the graphs looked like. So this is the position versus time in GlowScript. Here's the one from Tracker, and then here's a comparison. I put it into Excel of the GlowScript and the Tracker models. So, possible errors. The initial velocity was assumed to be 0 meters per second, but the initial velocity could have been slightly greater than 0 if the slinky wasn't dropped perfectly by the man in the video. So it could have started with an initial negative velocity. So, what does it mean? Does the bottom of your model slinky stay stationary just like in the video? Yes. The bottom of my model slinky stays stationary just like in the video. Since the force of the slinky going upwards equals the force of gravity going down, the net force acting upon the slinky before the top of it reaches the bottom is 0. So, in both the experimental and computational models, the bottom of the slinky stays stationary until the top reaches the bottom. So, when the top of the slinky does reach the bottom, there's no longer a tension force, and so the slinky begins to fall. Conclusion. The results obtained demonstrate that the slinky falls in a non-uniform manner due to its internal spring-like structure. The bottom of the slinky experiences an upward force due to tension in the spring, which causes the slinky to appear to levitate before collapsing to the ground. In the future, the experiment could be done underwater or in space to see how it affects the falling motion of the slinky. Overall, this experiment highlights the importance of understanding the physics principles in everyday objects and how they function.